Hi guys, my name is Ben and this is Pragmatic Software Engineering. In this video, we will be talking about recursion and iteration. As a programmer or a software engineer, we take a problem and we break this problem into smaller subproblems and we solve those smaller subproblems. If you recall what we did in previous videos, we've solved these subproblems with loops and arrays. And that is called an iterative approach or iteration. There is yet another approach to solve these problems. It is called recursion. While iteration draws its strengths from loops and arrays, recursion draws its strength from a function calling itself. The way the computer does this, iteration versus recursion, is fundamentally different. This is going to be a really exciting topic, but first, what I propose is that you stop this video, you find the strongest coffee you can make, brew some, come on back, resume, and we get started. What do you say? So when you're programming or you're doing any sort of software engineering, you first want to ask, what problem am I solving? A lot of times, if you're finding that the problem that you're solving is too hard, you're solving the wrong problem. And once you find the right problem that you're trying to solve, you decompose this into smaller problems that you can solve. This is a sort of, again, fundamental or fractal of software engineering, where you will see in a variety of different cases and a variety of different contexts, we will take a problem and break it down into subproblems and solve them. So the big terms we're going to be talking about today is iteration and recursion. So let's take a step back here and recall a couple of videos ago, we talked about for loops, we talked about while loops. And as of now, this is the way we understand these are the tools we have to repeat code. So as an example, if you're trying to learn how to program in Java or you're trying to learn how to code, you're going to watch every single pragmatic software engineering video. And you do that by a for loop, and your instruction inside the for loop would be watch. But as our good friend Arlo Guthrie said, there is a third possibility. It is called recursion. And recursion is a way for us to repeat code by having the function call itself over and over. And the function uses sort of variables and if statements inside. It uses that's called function scope, the things defined inside the function, to process these subproblems and yield a result at the end. Now, recursion is more expensive, but it is potentially easier to grasp in certain situations. Let me give you an example of recursion. So if we're researching a subject here, and we might be using Wikipedia to understand what that subject is and learn about that subject. So when we click on articles, what we do is we click on some article of how to code, and we don't know how to code. So we see some sort of Java on the page. Well, then we say, well, what the heck's Java and what the heck's Java's syntax? So we go into trying to understand what Java's syntax is. But then we realize we don't even know the fundamentals of programming and computer science. So then we go into the fundamentals and we learn how the fundamentals work. And once we figure out how the fundamentals have worked, we can now return to learning how Java works. And then once we're done with understanding the syntax of Java, we can go back on learning how to code. So you'll see here, we've divided this into steps, and we have a dependency of finishing these steps. We have to understand what Java syntax is and fundamentals before we learn how to code, and learning Java syntax has a dependency on fundamentals. So it's sort of, I'm trying to learn something, I realize I have to do more research on sort of things I don't know, so I do the research on those things, and it turns out there are more things I don't know that I need to understand. So I understand those fundamentals, and then I can get back to learning the Java syntax, and I can get back to learning how to code. So if you think back to our first video where we talked about the fundamentals, sort of the programmer's palette, we talked about functions, loops, variables. Now we're solving a sort of list of problems with functions instead of a loop. And this alternative way to solve this problem does not come without, its cons. So it does have some pros where this dovetails really well with certain data structures, which we'll get into later in this module. And using recursion, you can do a lot more instruction, you can do a lot more processing with less code. But the cons is the type of memory that this technique uses is usually more, and in certain implementations, certain languages, it can be slower. And finally, you can really catastrophically allocate too much memory and take down your program very easily if you do not use recursion with care. So it can be really easily misused. I recently tutored somebody on recursion, and I found that recursion can be a confusing topic to explain to somebody who is just learning it. So with this, I'd like to give you a couple of tips. These are sort of tips you get in, computer science as a whole, or software engineering, or some sort of best practices. These are just tips I've found for myself and others of how to use recursion more effectively. So the first thing you want to do is, because in recursion you basically establish a new scope to solve a subproblem, you want to surface when you should not spawn a new call to the function. So this surfacing and execution boundary really means you want to make sure that there is a case where you elect not to recurse anymore. And the second thing you want to do is you want to write a wrapper function for the recursive function so that you can easily separate this out in your mind and in your code. So here is a way I want to show you what's going on when we're computing factorial in a recursive fashion. So let me get my pointer here. We all know that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, and it equals 720. So when we do this with factorial, we spawn a new method call until we hit our base case. So if we take our first method call, what we really need to do here is 6 times whatever n, which is 6 here, minus 1 is, so 5. So then we do 5 times the function of n minus 1. And we go down again into 4. And we go down again into 3. We cascade into 2, and finally get to our base case of 1. And what we do is we accumulate what these evaluate to as we come back up. So 2 times 1, 3 times 2, 4 times 3 times 2, 5 times 4 times 3 times 2, and finally now we have what we expected right here, 6 times 5 times 4 times 3 times 2 times 1. We have it right here. Of course, I just dropped the 1 because it's not very helpful. But this is how we have taken a recursive approach to factorial. Again, what we've done is we've created a sort of new subproblem to solve until we get to our base case, and we have accumulated the results as we have gone back up. Here I have a quick program I've whipped up to compute n factorial. So I've created n as 6, and what I have is a for loop that starts at n and goes down till it's 1. And I have the multiplication doing the actual factorial work here. So we do output. We're basically accumulating that output equals output times I. I believe you can also change this to be times equals I, and this will do the same thing. And we finally print this out at the end. Cool. 720 is the correct answer. So recall I had 2 caveats, or caveats. I can't figure out how to say it, but we have 2 of those things. And one is to write a wrapper function, and the other one is write a case when not to recurse, called the base case. So let's write that wrapper function here, and that'll be static int factorial, and it will consume an integer called n. We will also create the recurse function, and this is the function that will actually be recursed, and we'll do n here as well. One of the reasons why I think having a wrapper function is really helpful and pragmatic is it kind of allows the user to call something that just handles the factorial recursion, but is in itself not recursive. It's basically a great way that we can handle this recursive function. We want to return recurse factorial n. And remember, we want to talk about what's the base case. When do we know we shouldn't recurse? And in this, I believe we do not want to recurse if n is less than or equal to 1. So we'll just return 1. Otherwise, we actually can recurse. And the way we'll recurse is we'll return recurse factorial. there's that recursion we're actually calling it here. N minus 1 times n. And if we run this, let's do this factorial n. We run this. We'll fire this off. Kaboom! We see both values are 720. So we've basically taken this factorial problem and we've done it with recursion. I'm going to give you sort of an extra little tidbit here of information. There are cases where you need to accumulate some sort of data. An example would be, for some reason, you want to be able to accumulate all even numbers that recurse factorial uses as n, as it goes down, as it gets multiplied. So let me just fill this out. If you want to accumulate some state, again, we're going to say we want to accumulate all even numbers that get counted down as we recurse. You'll see this in a lot of algorithmical questions, and I think it makes sense for me to explain this now. What you can do is you can begin to use the method signature to pass down a variable to the subsequent recursive calls. So as an example, what we can do is I'm going to use a data structure we have not used yet, but we'll be discussing it in the next video. It's called a list, and it's basically an array that you can add on to at the end. So I'm just going to call this even numbers, and I'm going to use this list and make it the implementation power unit called an array list. So basically all you really need to know is this is a list of numbers we can add to. So what we can do, we take this function method signature, we add a list as an argument. Make this list integer. And let me change this to integer as well. This is just generics. It's just syntactical things. We can say even numbers. And what we can do is we can say if n is divisible by 2, this is modulus. I'm not sure if we've talked about this, but modulus is the operator that is basically the remainder operator. So if we divide n by 2, if that remainder is 0, i.e. it is divisible by 2, then we can add this to the even numbers. Add n. Again, we'll add even numbers to every sort of reference to this recursive method. And let's take this even numbers thing out. Let's put this, well, let's leave it here just for this way. We're going to create int results equals this. We can print out here these even numbers. I really hope that printing a list is pretty here. We'll see though. Cool, it worked, and it is pretty. So, if we start from 6, all the even numbers that we see when we count down and do factorial are 6, 4, and 2. So here you're seeing, as we recurse through, we have a list that we're adding to. And I think this is common enough in algorithmical questions, whether it's in an interview, HackerRank, or in real life, that you should know about using the method signature to pass a state to the recursive call. In conclusion, recursion is another way we can solve subproblems in computer science and programming.
We have iteration, but recursion draws its benefits from sort of drilling down into the problem through all the dependencies and then coming back and resuming when those dependencies are satisfied. You'll tend to see recursion a lot in graph searches and tree searches in artificial intelligence due to the nature of that problem of drilling down and solving those subproblems. But we tend to prefer iteration because it is much faster. Please hit that subscribe button and like this video and tell your friends about us.